So yesterday we kind of hit on this dipole moments. So this is when we have a positive charge and a negative charge, and we're going to use an arrow to represent our dipole moment. So if we were to have the tail of the arrow is going to indicate the positive center. So if we had HCl, and the point will indicate the negative charge center. So we're going to draw some Lewis structures today. I'm going to draw them. I don't expect you to remember how to draw them just yet. That will be tomorrow. But we're going to talk about this. So if you will look here, again, here is the dipole moment. The arrow is pointing towards the more electronegative area, and then we have the tail, which gives us our partial positive. You will see these types of graphs in like organic chemistry. You see the dark red part, that is our more electronegative area, or our partial negative area, and this will be our partial positive, where that blue is. And you can kind of see that we have bright red over towards the O, so that means our O is the partial negative portion. So while we have, if we look over here at this very first water, you know that the bond between H and O is a partial is a polar bond, and we each H being the partial positive. Overall, the molecule would look like that. So that's the overall way. So each you have within your molecule, you can have polar or non-polar bonds, but then the overall molecule, we're going to show the polarity if it's polar or non-polar. So again, here we have, if we're looking at carbon dioxide, we see that there is, if we're looking over here at the color graph, we can see that there's no real set dipole moment. So when we draw this, you don't have any arrows. It would just, you would just put no dipole, or you would say that it's non-polar. Now within the picture that you have, you see that they have drawn that the oxygens are polar. They're pulling the bonds, but overall the whole thing is non-polar. And that is because we have this 180-degree bond, which is pulling those electrons and sharing them equally. Any questions over those? All right, so let's draw some. So it wants to draw we want to do the Lewis structures for hydroiodic acid. So if I have H and I have I, so which one is our most electronegative? H or I? I. It's got all those electrons in it, so it's pulling. We're going to draw the arrow, the head of the arrow by the I, and then we're going to put the tail by the H. And this is our partial positive, and I is our partial negative. Now if we draw nitrogen, which is a triple bond, so who is more electronegative? Neither, so this is not polar. And then finally, we have carbon, and we have some chlorines here and 2 fluorines. And it doesn't really matter which way you draw this. I've conveniently drawn our CLs and our Fs close together, but the overall 3D molecule each F would be close to the other F because of the 109-degree angle that's in between each one. So this is, who is more electronegative? Fluorine. So what's going to happen is we're going to draw our arrow pointing towards the fluorines. And we have our partial negative here and our partial positive. Any questions on that? Today's going to be a fast day. No. It's going to be fast, not that fast. Everybody good with that? Tomorrow we'll actually get into drawing the structures. Okay, so bond energies. We've kind of talked about this before. Remember, to break the bonds, energy has to be added, and to form bonds, we release that energy. So to determine how much energy is released when breaking or in a reaction, we have delta H is our bonds broken minus our bonds formed. So we learned different ways to calculate delta H. So what are the different ways we learned to calculate delta H? Huh? No, you're talking about Gibbs free energy. What? Bond energy, that's what we're talking about right now. What's the other ways we've learned? Energy of formation. So go think back to thermo. What were the different ways we found delta H of a reaction? Products minus reactants. All right, so products minus reactants. What else? How else would you find H? Hess's law. What else?
We can do delta T before and after.
So calorimetry. Q equals MC delta T.
Yeah.
And we can also use one other way. If I gave you a reaction and I said plus 65 kilojoules was given off, how could we determine how much that is per stoic? And now we're going to add bond energy. So in bond energy, this is kind of like a modified products minus reactants, except for bonds broken are on the reactant side, remember, minus the bonds formed, which are on your product side. So that's just one thing you just have to remember. It's reactants, or it's broken minus formed. Hess's law is where the flippy thing, where you flip the reactions.
Can you actually go over in detail? It's just you flip the reaction. If you have two reactions.
You have your overall you have a bunch of reactions. You have your overall goal, and you have to flip those reactions and their H's to get what you need. Okay, so are there any questions over that? We're going to do some of these, and then we're done. Okay. So if you will look, all bond energies are positive numbers. Okay? I want you to just make note of that. There was an AP question a couple years ago, and people calculated it wrong and came up with negative numbers, so they lost their point for that. So here it says predict the delta H for the following reaction. So I'm going to do this the long way, and then you'll be able to start seeing how to do it the easy way. So first thing I'm going to do is I'm going to draw this molecule. So we have carbon, and it has 3 H's and an N bonded to it. And that N is triple bonded to a C. How what?
Oh. If N has 4 bonds, then it shares one more electron than is necessary for it to have its octet.
Then you got to think of it overall. Don't think about those valence electrons. Think about it overall. And this is going to form, what do we form? We form a C with 3 H's bonded to it, and another C bonded to it with a triple bond N. So if we look here, we look at the bond energies that are given to us, we see that we have 3 HC bonds, we have 1 CN bond, and we have 1 triple CN bond. And then on the other side, we have 3 HC bonds, we have 1 CC bond, and 1 C triple N bond. Okay, so once you have that, then we need to go bonds broken minus bonds formed. So we have 3 times an HC is worth 413. We have 1 CN, which is 305. And we have 1 C triple N, which is 891. Yes, I'm getting there. And those are our broken, and we're forming over here. We have 3 of our H's, which is 413. We have 1 CC, which is 347. And we have 1 C triple N, which is 891. And if you can look and see, yes, you do have these. These two cancel each other out. These two cancel each other out. And we're left with 305 minus 347. So put that in the calculator and tell me what that is. Or you can just do it in your head. Negative 42 unit is kilojoules per mole. So yeah, it's you just do the shortcut. You see, oh, I have a bond here. I have a bond here. I have this bond here. I have this bond here. This bond. I can just subtract all the, or not even look at those because those are being broken and then formed, and so they're canceling each other out. Okay? So if you will look on the next slide, you'll see all those bonds are positive values. There is an asterisk over to the right-hand side for the CO bond. And if you will look, that is for any CO bond other than the bonds in CO2. If you have CO2, then that bond energy is 799. Okay, so anytime you see CO and it's not in carbon dioxide, it is 799. Huh? I'm not sure. Yes.
Why is there another CO
Another.
like CO 745 and versus 1072?
Is it a triple bond? I think it's a triple bond.
Why would
Why?
Yeah, why would a triple bond?
It's more stable, or it's available that way. So,
Which one for the NN and CN are triple bonds?
let me see. So you have NO, N double bond, N triple bond, C triple bond, and then C double bond. CN double bond.
And then, I'm sorry, the second CC at the top, the second one is the triple bond as well.
Yes, because you have your single bonds over here on the other side, and then you see the multiple bonds. So none of those on that multiple bonds are single bonds. They're all double or triple. Okay, so let's go do some of these. So here we go. Calculate, using your bond energies, calculate the delta H for the reaction. So how many CH bonds do we have? 4. And what is the value of that bond energy? Go to your table. 413. And we're going to add that to how many oxygens bonds do we have? Double bonds. We have 2, and what's the value for that? 495. So those are our bonds broken, and we are going to subtract our bonds formed. So how many CO double bonds do we have? 2, and what is the bond energy of that? 799. And we're going to add to that, how many HO bonds do we have? 4. And what is the value of that? 467. All right, do the math. Anyone got it? Negative 824 kilojoules per mole. So this next one, I'm going to kind of change it up a little bit. We have this reaction here, and I'm going to tell you that the delta H of the reaction is negative 109 kilojoules per mole. So, I want to know what is the bond energy of one NH bond. So, yes, you can go look on the table, but we're not going to. We're going to use our algebra to figure this out. So, we know we have bonds broken minus bonds, or bonds broken, yes, minus bonds formed equals negative 109 kilojoules per mole. We have bonds broken. So N2, how many N2 bonds are we breaking? 1. And what's the value of N2? Triple bond. 941. And we're going to add to that, how many H bonds are we breaking? 3. And each one is worth 432. And from that, we're going to subtract. How many NH bonds do we have? 6. And we do not know the value of that, so that is X. So solve for X for me. And X is going to equal the 1 NH bond. 391 kilojoules per mole. If you would have done products minus reactants, you would have come up with a negative 391, and you would have been wrong. You would have gotten your point taken away. So make sure when you have bond energies in your solvent form, that they're a positive value. Okay, so last one. Here's your problem. Using bond energies, calculate the delta H for the reaction. So go work that, and as you work it, I'm going to go ahead and stop this, and then I will add the answer here in a second.